Additive manufacturing has crossed an important threshold. We now have FAA-approved fuel nozzles flying in commercial engines, EASA-certified titanium brackets in service on aircraft, and qualified metallic parts supporting offshore energy operations. From a technical standpoint, Additive has demonstrated it can deliver functional, safety-critical components. But here's the crux. The limiting factor for broader adoption is no longer whether we can melt powder with a laser or an electron beam. The true bottleneck is certification and assurance. Regulators, insurers, and OEMs all want the same thing: demonstrable repeatability, traceability, and accountability, no matter where or by whom the part is produced. And that's the real challenge. Printing a geometry is straightforward. Proving that it is compliant across different sites, machines, and supply chains is not. That proof is where additive adoption slows, because the frameworks for qualification, certification, and liability are still catching up. In this episode, we're not talking about machine performance or alloy development. We're talking about the infrastructure that enables trust, standards, regulatory guidance, and certification pathways. We'll explore the current state of regulation, the integration of Industry 4.0 tools like digital threads and digital twins, the geopolitical and sustainability pressures shaping adoption, and the emerging models that may allow both small and medium enterprises and original equipment manufacturers to scale responsibly. Because for engineering teams, the critical question has shifted. It isn't, can we print this geometry? We already know we can. The question is, can we certify it, insure it, and deploy it at scale without duplicating costs across every region and application? The answer to that will determine just how far additive manufacturing goes in the next decade. So let's get into it. To understand where additive manufacturing stands today, we need to look squarely at the certification landscape. Because in regulated industries, the economics of additive are dictated less by machine throughput and far more by the cost of qualification. The starting point is the distinction between part certification and process certification. In the early days, every new geometry was treated as a new part that had to be dissected, tested, and qualified independently. That works if you're making thousands of identical turbine blades, but it's commercially unworkable for one-offs or small batches. Imagine trying to qualify a single aerospace bracket or a patient-specific implant with the same time and cost burden as a high-volume component. It simply doesn't scale, and that's why we're seeing the shift towards process-based certification. Rather than approving every geometry from scratch, regulators validate the entire process chain: machine, material, powder specifications, build parameters, and post-processing. Once that process is validated, any part built within that envelope can be considered compliant. The GE LEAP fuel nozzle is the flagship case. Certified by the FAA, it consolidated 20 brazed parts into one printed component. The win wasn't just the geometry, it was proof that if you lock down the process envelope for titanium Ti-64 in laser powder bed fusion, you can certify parts on the basis of process reliability rather than individual geometry. In Europe, Lufthansa Technik and Premium Aerotech extended this with their EASA-approved titanium bracket, the first load-bearing AM spare part certified for commercial aircraft service. Again, the key wasn't the shape, but that the entire process, from powder lot traceability to heat treatment and inspection, was validated under EASA's CMS 008 guidance. And there's Norsk Titanium, using wire-based directed energy deposition to achieve FAA approval for structural titanium parts on the Boeing 787. That showed that process-based qualification applies beyond powder bed fusion. Wire-fed AM can also meet the bar. Beyond aerospace, we have DNV's ST-B203 standard. This is now the reference for qualifying AM metallic parts in oil and gas, offshore and maritime. Operators such as Equinor are already using this pathway. The key here is proportionality. A pump impeller does not face the same scrutiny as a pressure-retaining valve body. So that's today's reality. Additive parts are flying, sailing, and operating, but only under tightly defined process-qualified envelopes, which leads naturally to the question, how do we make this scalable? And that's where Industry 4.0 tools come in. In practice, it comes down to three pillars: the digital thread, the digital twin, and in-situ process monitoring. And wrapped around those, two cross-cutting enablers: data interoperability and cybersecurity. Start with the digital thread. Regulators increasingly expect full traceability, not just the CAD file and a traveller, but the entire process history. That means CAD and build prep, the exact machine and firmware, parameter sets, powder lot certificates and reuse history, chamber conditions, full machine logs, in-situ monitoring outputs, all post-processing records, heat treatments, HIP, machining programs, plus inspection results from CMM, CT or other NDT. This isn't just best practice, it's codified. EASA's CMS-008 requires documented control of feedstock, parameters, and post-processing in aviation applications. ISO 52920 defines how an AM production site must qualify and maintain those controls. And ISO 52901 specifies the minimum information that has to be exchanged between supplier and customer when purchasing AM parts. In other words, the digital thread is now a compliance tool, not just a production record. Now the digital twin. Standards don't use that term explicitly, but they do acknowledge simulation as part of process validation. For example, ISO 52904, the practice for powder bed fusion in critical applications, makes clear that modelling and simulation can be used as supporting evidence for process robustness. And ASTM F3429 goes further, noting that simulation tools may be employed to demonstrate process capability. So while you won't find the phrase digital twin in the standards, the door is open. In practice, that means calibrating your models against real builds and test coupons, and then using them to predict residual stresses, distortion, or porosity. When you can show those predictions correlate with non-destructive testing, you can argue for less destructive testing. That doesn't eliminate qualification work, but it targets it, and that's where the cost savings come in. Then there's in-situ process monitoring. Every major machine OEM now offers melt pool sensors, photodiodes, or layer imaging. On top of that, you've got retrofit systems that provide quantitative height maps of the powder bed and fused surface. The key is not just collecting data, but correlating it. Build a defect library that maps signal anomalies to CT or metallography results, then define thresholds for intervention. That way you're not just saying, "We looked at the data." You're showing a documented chain. This signal means this defect, here's the supporting evidence, and here's how we responded. Standards are catching up here too. SAEARP 7068, still in development, is being written specifically to guide in-situ monitoring in metal AM. ASTM F3456 provides guidance on powder reuse, which is often verified with in-process monitoring and analysis. And EASA's CMS-008 already acknowledges monitoring data as supporting evidence. Of course, all this data only matters if you can move it and protect it. That brings us to interoperability. Right now, every machine OEM produces its own proprietary log formats. For a mixed fleet shop, that's a nightmare. That's why industry groups are pushing OPC-UA for AM and MT Connect extensions to normalize machine data for MES and PLM systems. Without this, you end up with terabytes of siloed logs regulators can't interpret. With it, you can present a coherent, auditable digital record. And finally, cybersecurity. In Additive, a compromised STL or parameter file is not just an IT problem, it's a potential structural defect. That's why the US NIST 8269 guidance frames AM cybersecurity as a product safety issue. Practical steps include signing parameter files, verifying them on the machine, controlling edits, and hashing log files to prove they weren't tampered with. Expect regulators and insurers to demand this level of digital integrity in the coming years. So here's the bottom line for engineering teams. If you want to make certification more economical, don't just look at faster lasers or bigger build volumes. Invest in data discipline. Build your digital thread in line with 52920 and 52901. Use simulation and digital twins in a way that aligns with 52904 and F3429. Integrate monitoring with correlation logic that anticipates ARP7068. Lock down your files per NISTIR8269. Because in the end, these Industry 4.0 tools aren't just operational upgrades. When you tie them to the standards, they become compliance assets. And that's what changes the economics of additive manufacturing in regulated industries. But regulation and monitoring aren't the only forces in play. To see where additive is truly headed, we need to consider the bigger external pressures: geopolitics, industrial policy, and sustainability. Let's start with geopolitics. Right now, the global regulatory landscape for AM is fragmented. In aerospace, for instance, Europe's EASA certification memorandum, CMS 008, lays down expectations for additive, everything from powder traceability to heat treatment and inspection. The FAA has its own frameworks, and while there are joint working groups, they're not fully harmonized. What does that mean in practice? It means that a part qualified in Hamburg might not automatically be accepted in Houston. That duplication is expensive and it slows adoption. In the energy and maritime sectors, things are a bit more streamlined. DNV's ST-B203 standard is now widely accepted for qualifying metallic AM parts in offshore and oil and gas applications. It scales requirements based on criticality, which is pragmatic. A pump impeller doesn't need the same qualification burden as a pressure-retaining valve. Lloyd's Register has also stepped in with its guidance notes for metallic AM parts, which insurers and ship owners already use when they audit suppliers. And in Singapore, 3D Metal Forge became the first facility certified by Lloyd's to print maritime spares. That certification wasn't about celebrating a new machine, it was about proving to insurers that these parts could be trusted at sea. In the US, the ANSI Additive Manufacturing Standardization Collaborative, or AMSC, keeps a roadmap of where the gaps are in standards, in powder reuse, non-destructive evaluation, design allowables. If you're planning your qualification strategy, looking at that roadmap is a good way to anticipate what requirements will be coming in 2 or 3 years. So geopolitically, we've got overlapping but inconsistent frameworks. Until regulators converge, FAA, EASA, CAAC in China, companies are stuck paying the price of duplication. Now let's move to industrial policy and economics. Additive isn't just a technology, it's also part of national strategies for supply chain resilience. In the US, the AM Forward initiative, launched by the White House, is aimed at pulling small and medium suppliers into AM adoption by using big primes like GE and Raytheon as anchors. On the defense side, the DoD's additive manufacturing strategy makes it explicit. AM is a tool for sustainment, for reducing depot repair times, and for avoiding fragile global supply chains. Singapore's NAMIC, the National Additive Manufacturing Innovation Cluster, is another model. Instead of expecting every SME to fund its own qualification program, NAMIC supports shared certified hubs where companies can plug in and build parts under validated process chains. That spreads the cost and lowers the barrier to entry. Europe is also funding similar projects under Horizon Europe, focusing on both qualification and workforce development. The common theme is this: governments see additive as a strategic lever, not just an industrial curiosity. And for professionals, that means you need to watch policy as closely as you watch technology. Finally, let's look at sustainability. For years, AM was marketed as inherently greener. Less waste, lighter parts, shorter supply chains. And in some cases, that's true. But regulators are moving past marketing into hard numbers. The EU Corporate Sustainability Reporting Directive, or CSRD, will require companies to disclose carbon emissions, Scope 1, Scope 2, and eventually Scope 3, in a structured, auditable way. That means if you're running AM production, you'll need to report the energy per build, powder reuse rates, scrap percentages, and even the logistics profile of your supply chain. And the EU Carbon Border Adjustment Mechanism, or CBAM, will start charging tariffs based on embedded carbon in imports like steel and aluminium. That's a direct cost driver. If you can prove that your AM process saves 80% of the titanium that would otherwise be machined away, that's not just an engineering argument. It's a compliance advantage. So here's the reality. Sustainability reporting is about to become part of your digital thread. Energy consumption, material efficiency, and reused data will be as important as build logs and CT scans when it comes to winning contracts. Procurement teams will score suppliers not just on cost and lead time, but on carbon footprint. Now, one more external factor we need to acknowledge is insurance and liability. Even if the regulator signs off, if your insurer doesn't accept the risk, you won't get to market. And liability in additive is complicated. If a part fails, is it the designer's fault, the operators, the machine OEMs, or the powder suppliers? Those questions aren't fully answered yet. That's why frameworks from Lloyd's Register and DNV are so critical. They don't just tell engineers how to run a process, they give insurers and customers the confidence to accept the parts. So, what's the takeaway from all of this? As a professional in additive, you need to widen your lens. Standards and process control are critical, yes, but so are regulatory harmonization, industrial policy, sustainability reporting, and insurance frameworks. If you ignore those forces, you risk being locked out of supply chains no matter how good your machine is. But if you understand them, you can position your company to be a first mover as these requirements become mandatory. Because the future of additive manufacturing isn't going to be decided just by engineers in labs. It's going to be decided in standards committees, in government policy, and in the offices of insurers and procurement managers. And if you're not tracking those conversations, you're only seeing half the picture. And if machines and policies set the stage, it's people that decide whether the play can actually run. Additive manufacturing is not plug and play. Printing parts that regulators and customers will accept requires expertise across multiple domains. On the design side, you need engineers trained in design for additive manufacturing, or DFAM. That means topology optimization, support strategy, lattice design, and an understanding of how orientation affects residual stress and surface finish. Traditional CAD knowledge isn't enough. On the production side, operators aren't just machine tenders. They manage powder handling, safety protocols, calibration, and build setup. For critical sectors, you need documented competencies, not just tribal knowledge. DNV's ST-B203 explicitly calls for operator qualification as part of site approval, and auditors now routinely ask to see training records as part of a facility qualification. Then there's quality and inspection. With in-situ monitoring, digital twins, and terabytes of machine data, the skill set is shifting. A modern AM inspector may spend more time analysing process data and CT scans than physically handling parts. That requires data literacy, statistical process control, and familiarity with monitoring platforms. National programmes are already addressing this. In the UK, the National Centre for Additive Manufacturing at the MTC has trained engineers from Rolls-Royce, BAE Systems, and many SME in advanced design and qualification practices. In the US, America Makes and the AMSC roadmap identify workforce as a top barrier, not just machines or standards. So what does this mean for professionals? First, treat workforce certification as seriously as machine calibration. If your operators and quality staff aren't trained and documented, you'll fail audits before you even get to mechanical testing. Second, engage with insurers early, show them your processes, map your controls to Lloyd's or DNV guidance, and make them partners in the journey. So with standards maturing, tools advancing, and external pressures mounting, the critical question becomes, how do we accelerate responsibly? How do we move faster without cutting corners on safety or trust? Let's break this down by stakeholders, policymakers, companies, and researchers. Start with policymakers. One of the most effective tools governments can use is the regulatory sandbox. This creates controlled environments where companies can test new AM approaches under regulator oversight. The EU has already piloted similar models under Horizon Europe projects, where regulators observe qualification in real time. This lowers risk for companies and helps regulators build familiarity with new methods like digital twins and in-situ monitoring. Another priority is harmonization. Right now, a part approved by EASA in Europe may still need redundant testing before the FAA signs off in the US or CAAC in China. That's duplication of cost and time. The joint FAA-EASA additive workshops are a good step, but the industry needs trilateral or even global alignment. Otherwise, AM suppliers will keep paying the price of fragmentation. Finally, policymakers must think about SME access. Big OEMs can afford full qualification programs. Smaller suppliers cannot. One solution is to fund qualified hubs, where SMEs can build parts within a pre-certified process chain. Singapore's NAMIC cluster is already doing this, spreading the qualification cost across many users. That's a model worth replicating. Now let's move to companies. The first priority is investing in quality infrastructure, not just machines. Too many firms buy a powder bed system, run a few demo builds and think they're production ready. The reality is that regulators and primes are looking for data discipline, a digital thread that covers powder lots, machine logs and post-processing, calibrated monitoring systems and simulation tools tied to real test data. That's what makes a line cert ready, not just the printer on the floor. Second, companies need to engage in consortia and standards bodies. The America Makes and AMSC roadmap is updated based on industry input. If you sit on the sidelines, you'll be reacting to standards instead of shaping them. But if you contribute, you get early visibility and a chance to align your practices before they're mandated. And third, don't go it alone. Leverage centralized hubs. Lufthansa Technic's AM Center is a good example. Airlines don't have to certify their own additive spare part programs. They can plug into Lufthansa's certified process chain and spread the cost. That's a model that works in aerospace and could be applied in medical and energy sectors too. Finally, let's talk about researchers. This is where the next breakthroughs will come from. Not in faster lasers, but in better predictive tools. Qualification by analysis is the end game. Proving a process through validated models and monitoring data instead of running endless destructive tests. NASA and NIST already publish open datasets on AM microstructures and defects to help validate these models. The more we share, the faster the standards can evolve. Then there's AI for anomaly detection. Right now, humans interpret monitoring data. By 2030, we may see certified AI algorithms acting as virtual inspectors, spotting defects in real time and providing regulators with the confidence they need to approve one-off builds. That's a major research frontier. And let's not forget open access test beds. When universities and national labs make their AM datasets public, it accelerates standards development and helps small and medium enterprises who don't have the resources to run hundreds of test builds. The Materials Genome Initiative is one example of how shared data can speed progress. Cross-cutting all of this are two more priorities: cybersecurity and sustainability. Cybersecurity is not optional. If a digital spare part file is compromised, you're not just talking about data loss, you're talking about a safety-critical defect. The US NIST IR 8269 already treats AM cybersecurity as part of product safety. Expect regulators to follow, and sustainability is coming fast. Under the EU CSRD and CBAM, companies will need to disclose carbon footprints and embedded emissions. For AM, that means reporting on energy per build, powder reuse rates, scrap, and logistics. If you're not building carbon accounting into your digital thread now, you'll be behind when procurement teams start scoring suppliers on emissions as well as cost. So what's the takeaway? For policymakers, create adaptive frameworks, harmonize across borders, and support small and medium companies through hubs. For companies, invest in digital QA infrastructure, participate in standards bodies, and leverage shared certification facilities. For researchers, push predictive models, AI monitoring, and open datasets into the mainstream. Acceleration doesn't mean taking shortcuts. It means building the infrastructure of trust, standards, data, cybersecurity, and sustainability. If those pillars are in place, additive manufacturing can scale into aerospace, medical, and energy supply chains responsibly. If they're not, AM will stay stuck in pilots and showcases. The choice is ours. But even with clear actions for today, we need to look further ahead. What might the additive landscape look like by 2030? There isn't a single path. There are at least 3 plausible futures, and which one plays out depends on how regulators, companies, and researchers act in the next few years. Scenario 1, the optimistic path: harmonized standards and certified digital twins. In this future, the FAA, EASA, and CAAC converge on process-based certification frameworks. ISO and ASTM standards like 52920 for site qualification and 52904 for PBF in critical applications are embedded into regulatory guidance. In-situ monitoring and digital twins are not just tolerated, but formally accepted as part of the certification evidence. And instead of every company carrying the full burden of qualification, we see widespread certified AM hubs. Airlines, hospitals, and energy companies outsourcing to facilities with validated envelopes. What does this mean in practice? In aerospace, maybe 15 to 20% of cabin and secondary structural parts are produced additively, with lead times cut from months to days. In medical, patient-specific implants become routine, using pre-approved lattice structures reshaped for each patient. In energy, turbine OEMs repair and remanufacture blades with AM as standard practice. In this scenario, additive doesn't beat traditional manufacturing on unit cost, but it wins on agility, time to part, and regulatory acceptance. Scenario 2, the fragmented path: regional standards, stalled adoption. Here, FAA, EASA, and CAAC continue to diverge. The standards exist, but regulators interpret them differently. A part qualified in Europe still needs duplicative testing in the US. Small or medium companies can't afford the cost of entry. Insurers demand their own qualification evidence. As a result, AM adoption remains limited to showcase parts, similar to GE's LEAP nozzle, Lufthansa's cabin brackets, but not widespread production. In practice, aerospace adoption stalls outside of a few high-profile programs. Medical implants remain niche because hospitals can't navigate the liability. Energy operators stick with pilot projects. Additive is seen as impressive, but too slow, too costly, and too fragmented to scale. Scenario 3, the tech-driven path: AI certified monitoring unlocks scale. In this case, regulators formally approve certified AI algorithms for in-situ monitoring. These become virtual inspectors, replacing large amounts of destructive testing. Standards like SAEARP 7068 for in-situ monitoring, once finalized, give a common framework. Data interoperability matures through OPC-UA and MT Connect extensions, allowing cross-platform analysis. And cybersecurity, guided by NIST IR 8269, becomes a compliance requirement, ensuring digital spares can be trusted globally. The impact is huge. Smaller companies can finally enter regulated supply chains by leveraging certified monitoring systems rather than funding full-scale qualification programs. Aerospace MROs set up qualified AM cells at airports. Hospitals print surgical implants locally under validated monitoring. Defense and energy deploy certified field printing units where spares are needed most. So what does this mean for you as a professional today? It means you can't just prepare for one scenario. You need to build flexibility into your strategy. In the best case, harmonized standards open the door. In the fragmented case, you may be stuck with duplicative costs. In the tech-driven case, the advantage goes to those who can integrate monitoring and data-driven QA today. The common thread is trust. Whichever future emerges, additive only scales when regulators, insurers, and customers believe the parts can be trusted. And that leads us to our final point: what all of this means in practice. We've covered a lot in this episode, from process-based certification and standards, to digital twins and monitoring, to geopolitics, sustainability, and future scenarios. So let's step back and ask, what's the real takeaway? It's this: the barrier to additive manufacturing adoption is no longer the laser or the alloy. It's trust. And trust isn't built by running faster machines or larger build envelopes. It's built by demonstrating to regulators, insurers, and customers that your process is consistent, traceable, and defensible. That's why standards for site qualification and for energy and maritime applications matter. That's why digital threads, monitoring, and cybersecurity are no longer optional. And that's why training operators and inspectors to certification-grade competencies is as important as buying the next machine. So, if you're an engineer, align your work with published standards and start correlating your monitoring data with QA outcomes. If you're a manager, invest in your people as much as your hardware. If you're a policymaker, push harmonization and make sure smaller companies aren't priced out. And if you're a researcher, focus on predictive models and open data. They're the foundations of qualification by analysis. Looking out to 2030, additive could be mainstream in aerospace, medical, and energy, or it could still be stuck in showcases. The difference won't be technical capability. It will be whether we've built the infrastructure of trust. So the real question isn't, can we print it? We already know we can. The real question is, can we certify it, insure it, and deploy it at scale? For the companies and professionals who answer yes, the next decade of additive manufacturing will be full of opportunity. Thanks for tuning in. I'd love to hear your perspective. Where do you see additive delivering real value today? Leave a comment, share your examples, or highlight where you think the biggest gaps remain. And if you found this useful, please subscribe so you don't miss the next deep dive. Because the future of additive manufacturing isn't just about making parts. It's about building trust. And doing so at scale.